Hello everyone, today we're talking about limits at infinity, section 12.4 in our book. So now we're basically finding the limits at infinity of these functions. So that means as x goes all the way out to positive infinity, what value is my function going to approach? So in the first one, if the degree of my numerator is the same as the degree of my denominator, then the limit is just going to approach the ratio of that. So kind of like, just like the horizontal asymptotes back in rational functions. So they have the same degree, so it's basically going to approach 2/5 all the way out at infinity. So no matter how far x goes out, it's always going to approach 2/5, and you'll see in the line here, in the graph here, I've already graphed it for you. This blue line here is the line y equals 2/5, and you'll see that as the function goes out towards positive infinity, it's going to approach the line y equals 2/5. So that proves that as long as our degrees are the same and we're going out to infinity, basically we're just looking at the coefficients of those two variables. Now they want us to find a limit. In this case, we have a larger degree on the numerator than in the denominator. So again, just like back in horizontal asymptotes, when it was larger, we said, well, it doesn't have a horizontal asymptote, if you remember, because my limit goes to infinity. So if I have a larger exponent on the numerator than the denominator, see this one's 4, the largest one down here is 3, then I'm going to go to infinity. If you want to think of it as the 3's canceling out, I still have an x left in the numerator, means I'm going to infinity, right, if I plugged an infinity in for x. So that just means as my x values go out towards infinity, my function is just going to keep on rising. It's never going to approach a number. So as x goes to infinity here, we're going to infinity because the numerator has a larger degree. Okay, next we have the denominator with a larger degree. So just like with the horizontal asymptotes, you have a larger degree in the denominator, right? We're going to approach 0. And that makes sense because 3 divided by a very large number is pretty much going to be 0. So you'll see it on our graph. You'll see that as our x values go out towards positive infinity, our function is definitely going to approach 0. So larger degree in the denominator, our limit is going to approach 0. Okay, here we have two different limits. So again, we can go back to use our limit laws, and so we can do the separate limits. So if I do limit as t approaches infinity of 1 over t minus the limit as t approaches infinity of 2t over t minus 1. Well, here my denominator has a larger degree, so that's just going to go to 0. And here my numerator and denominator have the same degree, so I'm just going to take the ratio of those two coefficients. So this one's 2, this one's 1, so 2 divided by 1 is 2, meaning the limit of this function, if you plugged that whole function into your y equals to graph it, so the limit of that whole function as x goes to, tx goes to positive infinity is going to be negative 2. So here I already have the graph drawn for us. And here this blue line is the line y equals negative 2. And you can see that as x goes out towards positive infinity, this function is going to approach the line y equals negative 2. So it proves that we can just use our limit laws there and do the separate limits in order to come up with our final limit at infinity of negative 2. Now they want us to know if the sequence is convergent or divergent. So if it's convergent, that means it has a limit. So if you can do the limit of a sequence, then that means that it is convergent if there's a limit. If you can't find the limit, then it's divergent, and you have to explain why, at least in these examples here. So basically, our sequences converging or diverging means as you go out to infinity. So as my x values get really large, or as my n values get really large, is my series going to converge to a point, or is it going to constantly diverge, right? Is it going to go away from each other, or is it going to converge at a particular point? So, just like before, let's get it all into one function, so I can distribute here, and I get an equals, I'm really only worried about the largest degree, right? I'm not worried about what comes after the largest degree. So I think you'll agree that if we distribute all of these n's out, we're going to get 24 on the outside still, over n cubed. And the numerator here is going to have n cubed, 2n cubed, because we have a 2n times n times n, so we're going to have an n cubed as the largest degree. And then there's going to be stuff after it, but we're not worried about that stuff because we're only worried about the largest degree and the coefficient of that largest degree, right? Everything else will have a smaller degree, so they're not going to impact our limit at infinity. So I'm going to go one step further and see here I have 24 times 2n cubed, so that gives me 48 n cubed. And then I know I would have stuff after that, but it's not important because this will be the largest degree, will be a cube. And then in the denominator, I'll have 6n cubed. So now I'm down to something where I can see, okay, my numerator, the largest degree is 3. The denominator, the largest degree is 3. So as my sequence goes out to infinity, all we're looking for is the ratio of the leading coefficients. And since 48 divided by 6 is 8, the sequence converges at 8. So as I go all the way out to positive infinity, my sequence converges to 8. Finally, they want us to determine if it's convergent or divergent. So this one's a whole lot easier to see right off the bat, right? Because our numerator is larger than our denominator, so our limit is approaching infinity, right? So as x get really large, our limit's going to go to infinity, meaning since we do not have a limit, it's divergent. So again, divergent because our limit is infinity, right? Larger degree in the numerator than the denominator. As we go out, as x approaches positive infinity, our limit also goes to infinity, meaning we have a divergent series. So go ahead and try the example problems that accompany this in the PowerPoint, and we'll talk about it in class tomorrow.